All right, everybody, this is the Ice Bucket Challenge. And here we go. Blah, 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 bunch of words. And there it is. Hey, there's old Bart. So there's two things we're looking at today, guys. We're looking at the slowest this bucket could go and water doesn't fall out, as well as the fastest this can go and not break that rope that can only support a maximum of 21 newtons. 22 newtons breaks the rope. So Bart can't swing it so fast that the tension is too great that it's going to break the rope, but he also wants to swing it slow enough right there so the water's about ready to fall out, but it can't quite fall out. So the story is, let's do the critical speed first, which is the slowest speed we can go, and that stuff doesn't fall out. So at the tippity top of that circle, normally as Bart is swinging that thing around at the top, you would have, let me just draw one over to the side over here. Draw a pink one. So if this is going around and around, let me just draw something to the side right over here. So as this bucket goes around in a circle like this, and here's a string tugging on it. Normally, there's a tension force down on this. So let me do that in green. So that would be a tension force that Bart's pulling with. And plus we also have gravity acting on that, and gravity is dark green over here. And that's just the mg, or pull of gravity. But at the very slowest speed that he can go, Bart doesn't have to pull at all on that thing, because what keeps changing the motion of the water is just gravity at the slowest speed. So at the very slowest speed, gravity is the only thing changing the motion of that water. So it's the only centripetal force there is at the slowest he can go over the top. Turns out we don't have to know the mass there to find the critical speed, because that's what we're really looking at, is the range of speeds that the rope doesn't break and it doesn't leave the bucket. So first we're doing the slow one. So it turns out the mass doesn't matter there. So to find the velocity, or the slowest speed it can go, that's just your G times your R. And so in this case, we're on planet Earth. Even Springfield there is in planet Earth. So that's a 9.8 meters per second squared. The R in this case is 1.63. But remember, that equals V squared. So you got to do the square root of everything to get rid of that little square thing there, right? Oh, grand, there's a Java update. I can't wait to do that. So then to find just the velocity of that thing, it's the square root of that whole dealio. All righty. So in my case, I got to get my calculator out here. There we are. Clear. All righty. So I'm going to do second function square root parentheses 9.8 times 1.63 in parentheses, but I am 3.9996. It's 4.0. Okay. So here's the story. As long as Bart keeps that going at 4 meters per second, water's not coming out. That speed drops below 4. Now there's slack in the line because gravity's yanking it down out of that path hard, and water's going to come out and ice is going to dump everywhere. If he goes at 4.2 meters per second, not a problem. There's only a little bit of tension. If he goes at 8 meters per second, now there's more tension, but so the water's not coming out. So we already answered the first question, the critical speed of the slowest we can go, so no water comes out of that, and that's the 4 meters per second. At the bottom, it's a different story, because this bottom is when the bucket's at the bottom down here, sure, mg, it's the same size, it's downward, but now the tension is actually opposite of that because he's pulling up on it. And the tension has to be bigger than the mg, otherwise it wouldn't be changing motion. So when we're looking at our business of our FMA, because anytime we have a change in motion, because we're changing the motion, that is an acceleration. We're talking about a FMA, the sum of all forces. So we're gonna have to sum up all the forces here at the bottom. Oh, the reason I'm doing it at the bottom is that's where the tension is going to be the greatest. Here, gravity pulls some of the tension off at the top, so there's not as much tension. Here, the tension is fighting gravity and changing the direction. So it has to be bigger than this, one to balance, and two to change the motion. So if it's going to break, it's going to be at the bottom. And we don't want 22 newtons of tension, because that's going to break it. So the fastest we can go is whatever speed to keep it at just 21 newtons right over here or less. Well, at the fastest we can go, we're going to keep it right at 21. So the sum of all forces is the centripetal force over here. So the sum of all forces, same as that we have over here, is a centripetal force, which is the mv squared over the r. So now I have to sum up all my forces. So I have the tension going up minus the gravity going down, and that equals my mv squared over the r. All right, so the mass doesn't cancel out quite so easily because then it's in the tension there. So I'm going to leave it alone. And what we're doing is solving for that v anyway. Okay, so first I'm going to divide out by the mass, because I got to solve for the v again. So I'm dividing out by the mass, and what I do to one side, I do to the other. I have to do to both. So the mass is on the bottom. But now I got to multiply times the radius. So I'm going to times the radius here. What you do to one side, you got to do the other, times the r over there. And then the last thing is I got to do the square root, just like I did over there, the square root of both sides to get rid of that. And so it's going to look a little complicated on this side by the time I do all of that. So if I rewrite everything that I just did over there, that's my tension, my maximum tension, minus the mg. Whoops, remember the r is underneath that whole square root thing. So now I got to put a parentheses in there because that's going to be times the r, but it's divided by the m. Okay, so we're just flipping that around. All right, now that's going to be the velocity. So now we're just plugging in some numbers over there. So plugging in the numbers for me for the maximum speed, we can go and not break the string. So now I got to go, the tension over here is going to be 21 is the maximum tension I can have. I'm going to leave off my units because I'm out of room here. The weight of that thing is 0.14 times the 9.8. Because that's the G thing. And then I still have to do, oops, I got a double parentheses, man. And then I'm going to put an R over here. The radius of that thing is 1.63. Remember, we're still under the parentheses. It's long and ugly, but that's how I'm going to roll. And then on the bottom, the mass is the 0.14. Okay. All righty, and clearing that. So second function, doing my square root thing, and yikes, I got a lot of parentheses. This is going to be ugly. Hope I don't screw it up. So I'm going to do a double parentheses, 21 minus 0.14 times 9.8 into my first parentheses, now times the r, the 1.63, and then I'm dividing that by the 0.14 into my last parentheses. So now it's all under the square root function. And hey, I didn't get a syntax error. Hallelujah. Okay, so I'm going to put my answer right up here. So it says my maximum velocity is 15.1 meters per second. Okay. All righty, guys. Cross your fingers. I'm feeling pretty good about this. Oh, I got to stop my annotation here. And so I'm going to end this. So I got 4 and 15 to put in for my numbers. 4 for my slow speed, 15 for my fast one. All right. Okay, that's me. Oh, man. I don't know why this thing does that. Minimum speed, 4.0 in meters per second. There it is. And then I've got, okay, my maximum was 15.1. I could probably get away with 15, but I'm going to put the 1 just to show off. And I'm submitting. Bam! Minimum speed is 4. Nailing life. Maximum speed is 15. They're wrong. It's 15.1. So my answers are good enough. Well, thank you. There I am, stopping my share. That's how you do the ice bucket challenge. All righty. Have a good one.